we've been talking about eigenvectors and eigenvalues and linear operators. It's time to add more structure to our vector spaces. So this is a thing that we're doing in a very deliberate way. We introduced our vector spaces and we put just absolutely the minimal amount of structure. The addition of vectors, multiplication of vectors by numbers. With that, you could talk about linear operators, we could talk about matrix representations, we could talk about eigenvalues, eigenvectors, invariant subspaces, all kinds of very interesting properties. Kernels, range, surjective, injective, invertible operators, inverses, all that. You would say, wow, you've done most of it, but not true. We have still to add a little more structure. In particular, with all the axioms I've given you so far, if somebody would come to you and say, what is the length of this vector? You would say, oh, nobody spoke about length so far. So we're going to try to see what are the structures that allow you to talk about length and why would you be interested in using those structures. In fact, that structure, which is called an inner product, is a very interesting structure and allows you to talk about lengths, to talk about norms of vectors, and then, moreover, it allows you to define all kinds of new operations that give rise to what are called adjoint operators, with which you can define what operator is Hermitian, is unitary, projection, orthogonal projection operators, orthogonal spaces, all kinds of very useful stuff. So this is the time where we add a bit more structure to the complex vector spaces, and it will be a very good thing to do. So we're talking about inner products, therefore. Inner products. So it all begins with this attempt to define length. So we're going to talk about this thing for real vector spaces first, because this is a case that you all have seen before. The complex vector space is only a little different. That difference creates that in the axioms that we will list, it creates a tremendous richness and tremendous new possibilities just by changing an axiom a little bit. So what we're going to do is motivate these things by considering the vector space Rn. Real vector space Rn. So a vector in this vector space is a collection of n real numbers, and we will denote it as, say, A. We don't put arrows on vectors unless necessary. A2, A1, A2 up to An. So this is your vector. And if you remember your intuition from ordinary geometry, the length of a three-dimensional vector is the square root of the squares of the components. So we'll call the length of A we'll call it A with some sort of absolute value. That doesn't mean absolute value of the number A, because A is a vector. It means the length of A. And therefore, it must be defined. And it's taken to be the square root of A1 squared up to An squared. So you sum the squares and take the square root. Now, people, when they saw this, they decided to invent a product, and they didn't call it an inner product, called it a dot product, and said, look, it looks to me like a nice thing we could do here. We could say that the length squared of the vector is the inner product of the vector with itself, and that thing, therefore, is going to be equal to a1 squared plus up to an squared. So this length squared is now not thought as a recipe, add the square of the first component second, but as a result of doing an operation with A with itself, squaring it in some way, in a way that is called a dot product. And then the last generalization came when they said, well, you know, we could do this in general. So given two vectors, A and B, we would now add a vector B, which is going to be B1 up to Bn. You could add and say that this is going to be A1 B1 plus A2 B2 plus A3 B3 up to An Bn. And that would be an interesting definition of a dot product. It's the definition you are familiar with. So there it is. That's a dot product. Now, when you see this thing, you say, this is great. It's very explicit. You can calculate it. There are lots of things you can do. Any vector, you calculate the length squared, take the square root, take the dot product, and then there will be some things that are true with this definition. Maybe some theorems hold. Now, the whole purpose of a more advanced discussion of the inner product is to absorb, not to give a definition. Precisely that's what we don't want to give. We want to state what are the axioms that an inner product should satisfy in such a way that this may satisfy all the axioms, but then there may be some other things, some other definitions that work. This is admitting to yourself that maybe you stumbled in a nice definition, but that definition may not be the most interesting one. There may be other definitions. And therefore, you sort of look at what you like about this and just state what you like the inner product to do, and then see if there are other things that do it. And then you may be in for a surprise, that there are more things that do it. Moreover, once you've defined it this way, if you prove that this inner product satisfies a property, and somebody comes with a different definition of an inner product, you wouldn't know if that property is satisfied. But if we all agree that there are some desirable properties of inner products, then we have a much better tool to work with this. So let me try to do that. So I will state some axioms that I want for the inner product on a real vector space. So axioms for inner product on a real vector space. So this inner product will be written as a dot product. And look, the first axiom that I will put is that if you take any vector A and you dot it with itself, you get something greater or equal than 0. It's true here and seems reasonable. Then we could use, for example, A dot A to be the length squared because it's positive, and we would have a notion of this. So however you define your dot product, it should do this. Then the next axiom is going to be that if A dot A is equal to 0, then A is equal to 0. In fact, it goes either way. But this is very interesting. You say if any vector has A dot A equals 0, which is going to mean that the length, or what we call the length, is 0, it's the 0 vector. This is such an important property. It will be the property you will use for half the proofs that you ever tried to do in linear algebra or in quantum mechanics related to operators. So if you manage to show that an operator or a vector, I'm sorry, dotted with itself is 0, then you know the vector is 0. And that is satisfied here. If this sum of squares is 0, since each square is a positive number, each one must be 0, and therefore a1, a2, a3, up to an are 0. So this is nice as well. Then we want another property, 3a with b plus c. You should distribute ab plus ac for a dotted with alpha b, where alpha is a real number, should be equal to alpha a dot b. So these are things that you intuitively know and are satisfied by this definition. You want to compute the dot product of two vectors, the numbers go out. Finally, we come to one property that is very peculiar, but we'll take it to be true here. It will be changed. A dot B equal B dot A. Certainly satisfied by this. And all right, these are all our axioms. Then we can say length of a vector is defined to be the square root of A dot A. It's a definition at this moment, and this is called the length of A. Now you could say, well, a good question would be how much does this set of conditions forces us to define the dot product this way? Well, we've seen that this satisfies all this product, but does it force you to do that? And the answer is no, it does not force you to do that. You could define A dot B to be C1, A1, B1 plus C2, A2, B2 plus Cn, An, Bn. And this property would work equally well if all the Ci's are positive. So you put 1, A1, B1, 2 times A2, B2, n with An, Bn. It would do all these properties. This will be true. This will be true. We'll distribute exactly the same way. We'll do that. So it doesn't force you to get this inner product. So you could ask, what's better about this inner product than this inner product? And there's some things that are nicer, but you may one day consider that one, and it will be a good inner product. What goes wrong if one of the C's is 0? I'll let you think about it. One of these axioms goes wrong if any one is 0. So these axioms guarantee a property that is tremendously important. It's called the Schwarz inequality. Schwarz inequality. What is the Schwarz inequality? It's a statement that compares the inner product of two vectors to their norms. So it's a very interesting statement, and it's a very powerful statement. It's a theorem that says that A dot B is less than or equal than A B. That's the claim. Now, it's very important that you look at it and see exactly what is being said in this equation. It's not all that obvious. First, these bars. This is the length of A. So whatever this bar in here means A dot A square root, B dot B square root. What do these bars mean? Watch out. A dot B is a number. So maybe that's something I should have emphasized here, that A dot B belongs to real. A dot B belongs to the real number when A and B belongs to this vector, real vector space. So the dot product is a number. So A dot B is a number, and here it would be the absolute value of a number. So here you have the bars can mean different things. If a bar goes for a number, then it's the absolute value. If the bar contains a vector, is the length of the vector. So here it's saying that the number A dot B, its absolute value, is smaller than the products of the lengths of the vectors. This is something that you probably have some intuition from this formula. In this formula, the way people explain this to you is that if you have two vectors, the dot product can be shown to be equal to the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle in between. So in R3, for example, in R3, you know that A dot B is length of A, length of B times cosine phi. So since cosine phi is less than or equal to 1, this number, as the magnitude of this number, is less than the magnitude of A times B. And that's the statement of the Schwarz inequality. Now, you would say, therefore, oh, well, then to show the Schwarz inequality, I need to use the dot product you have. So the Schwarz inequality is probably true for this, but how about for this? What I'm going to claim is that given that the Schwarz inequality actually follows from these axioms, it will be true for any inner product you define that satisfies these axioms. In particular, this one, in which you could not write a formula like this. This formula would not be allowed. So the proof of the Schwarz inequality will be based just on these axioms. I will do this one, though I will not do the one for the complex vector spaces. So let's just do this one and try to understand what's going on. The way you go about proving this is again through this statement that any vector has positive length squared, A dot A is 0. So consider a vector B and a vector A. And now we will build the orthogonal projection here. That is, we will think of A as built from some A parallel that goes parallel to B and some A perp that is orthogonal to B. So any vector A that is not parallel to B can be written as the addition of an A parallel to an A perpendicular. And I want to write a formula for A perpendicular. So what is A perpendicular? A perp is A minus A parallel. A minus A parallel is this vector. And what is A parallel? Well, A parallel is a vector along B. So, and what is its magnitude? Well, you have to get the component of A along B. Now, in 3 dimensions, you have an intuition of how you do this, but here may be a little less intuitive. But you go with the flow and say, well, what I should do, I should take the dot product of A dot B, because that gives me how much there is of A along B, and then I will divide by B dot B. And this is equivalent to, if you think about it in ordinary intuition, to do A multiplied with the unit vector along B times the unit vector along B. Because B dot B is the length squared. So one factor of length for this one factor of length for that one, and you're doing this intuitively, which is intuitively the component of the vector A along B. You take the dot product and you multiply by B. So as a check that this is correct, you can multiply A perp with B. How much do you get? You get A dot B, and here you get minus A dot B times B dot B over B dot B, and that's 0. So this thing is fine. That's A perp. It is perpendicular to B. We've checked that. Now, okay, this is an interesting vector, A perp. It exists. And now, the reason, you see, the reason this inequality is an inequality is because A and B form an angle. If A and B didn't form an angle, you would get an equality. Therefore, it's reasonable to think that the reason this inequality is true is because A perp is non-zero. Because A perp being non-zero means that A is not parallel to B. And therefore, we should try just to see that A perp squared, because of the first axiom, must be positive. So if we'll just compute that. So A perp dot with A perp must be positive. So how much is it? Well, A, you would have A with A. Now you would have the double product because the order doesn't matter. So imagine two factors like this. You have minus twice A dot B times another A dot B over B dot B like this. So it's the product of this times that, with a factor of 2, so A dot B squared, B dot B. And then I have this factor squared. Well, this is going to be a plus A dot B squared. And you have B with B, and B with B squared. So you will have just a B dot B in the denominator. So these two factors are actually the same. Those two summands are the same, so they can be combined. And then you get A dot A minus A dot B squared over B dot B. And this thing must be greater or equal than 0. So basically, we're really done. Let's move the second term to the right-hand side and flip the equation. So you would have A dot B squared over B dot B is less than or equal to A dot A. So B dot B is a positive number. That's axiom number 1. Therefore, I can multiply this inequality by B dot B to get A dot B squared is less than or equal than A dot A times B dot B, or in perhaps more recognizable language, length of A squared, length of B squared, A dot B squared. And we're there, basically. You take the square root. You can take the square root into positive numbers. These are all positive numbers, and inequality doesn't change direction. And then you put here length of A, length of B, and here you take the square root, but the positive one, and therefore you need to put the absolute value term, and there we got it, Schwarz inequality. It has been proven. The only way it would be saturated, and you always ask, when does it saturate? What it means is, when is it not an inequality, but rather an equality? And the answer is that it would saturate if this would be an equality, and that would be an equality if the vector A perp would be 0. And the vector A perp being 0 means that A is actually up to a number equal to B. So A and B are parallel. So saturation, if and only if A is some constant times B, real number. So that will saturate inequality and make the, it's a very peculiar case. In general, it is an inequality, but it may happen that for some particular vectors, the inequality becomes an equality, and that particular circumstance is only for parallel vectors. So see the lesson here. We never had to use the formula for the inner product to prove the Schwarz inequality. That's what we gain by this analysis. We've abstracted away the key properties that make something as interesting as the Schwarz inequality hold, and we never had to use this, the cosine phi or anything like that. We wrote things inspired by our intuition, but then the end result was that the Schwarz inequality is a very general thing that happens to be true whenever you have this inner product.